Hey everyone, I want to thank you for attending my talk on cryptography titled Magic Crypto Dust. Just a little bit about me. I'm Daniel Profancic. I'm a technical director here with the AppSec side of the house at Optiv. Uh, there's my contact information, my Twitter handle if you want to follow me on there. Appreciate it. A little bit about me. I've been in the industry for about 22 years, exclusively offensive security for about 13, 14 years. Been with Optiv for about 9 months. A little bit about the agenda. What we're going to talk about today is the problem is that, you know, I know I titled it Magic Crypto Dust, but a lot of developers that we find, kind of treat cryptography as kind of magic, and uh, it's not. It's not magic. And then also treat it as a black box, right? Something goes in and something comes out, and we kind of don't know about the in between. Is what we see. Um, and while cryptography is highly beneficial, there are a lot of ways that it can be implemented incorrectly that can actually cause more vulnerabilities than it started out with. So we're going to talk about encryption, just give some explanation. We're going to talk about issues that we've seen, and then how we fix that. What's the proper way to do cryptography? As I said, it's encryption's not magic. There's no dust you can just sprinkle on something, or some, powder you can, give to it that's going to make it, all go away and, easily solve all your problems. Another thing I want to clear up is that encoding, hashing, and encrypting are completely different things, but that oftentimes also gets screwed up as to, you know, um, whether encoding and hashing is good enough, and whether that's encryption. But it's not. Um, things like base 64, MD5, SHA-1, or even what we see as plain text. Uh, that seems obvious, but often not. Um, those aren't encryption because it can be reversed. So as I said, hit plain text. We still see that in databases and over the wire, um, and that's not just because you have to get into the database or you have to intercept that traffic. Plain text is not safe. So as I mentioned, encoding. So base 64 is the most common one. Um, this is just easily reversed back to plain text. And so though it looks esoteric, it looks encrypted, it's not encrypted. This is easily reversible. Now, your hashing algorithms like MD5, SHA-1, SHA-256, SHA-12, um, SHA-2, those are one-way hashing algorithms. So though you can't easily reverse it, things like MD5, SHA-1, they suffer from multiple issues. One is you can brute force them to get the result. Uh, there's things out there like called rainbow tables that have literally all the values that you could possibly use to find the value of these. As well as they suffer from what we call hashing collisions. So these algorithms will have, they were meant to have one value that is spit out, and that be unique, right? The hashing collisions are where two values can have the same hash, and that's what makes things like MD5 and SHA-1 vulnerable. So encrypted is like this, like an AES 256. This is the binary result of that. And so this uses a unique key and can't be reversed without that key. So let's talk through a little bit about different encryption types and how that works. So one, as I mentioned before, like AES 256, is a symmetric encryption algorithm. Basically, there's one key that decrypts and encrypts both the ciphertext and back to plain text. Some examples, like I said, AES, 3DES, Blowfish, IDEA, and also a stream cipher is an example of that, where each byte is encrypted altogether, or one at a time. A block cipher, so like your ECB mode or CBC mode, is where it's broken down into individual blocks, and then but you have to have a total size length for your block size, and so you add padding to the end of that block, and there's different ways of doing that, and we'll dive into that in a little bit. The main advantage of a symmetric encryption cipher is that it's very fast, and speed is an advantage. The problem with it, though, is, as I said, the same key can encrypt and decrypt. So key distribution is a difficulty with this type of encryption method. Also, known and chosen plain text, there are different cryptanalysis methods, and we'll dive into that in a little bit, that have some weaknesses depending on the mode and the way that symmetric encryption is implemented. Asymmetric encryption is basically where there's what's known as a public key and a private key. So one key to encrypt, one key to decrypt. It's great for confidentiality and authentication, and this is how like your SSL or TLS is going to work. So it will use an asymmetric encryption algorithm to share the key, because as we mentioned on the previous one, symmetric, the key distribution is the biggest problem. So it will use asymmetric encryption to pass that shared key, and from that point, because of the speed, it will use a symmetric algorithm. Some examples, Diffie-Hellman, DSA, RSA, that sort of thing. As I mentioned, key privacy is the biggest advantage to asymmetric encryption, but there are also many weaknesses: man in the middle, side channel, timing and type attacks. As I mentioned, it's also slower, so computationally expensive. And then there's, it seems far-fetched, but quantum computers can actually, and entanglement theory, you can actually decrypt the key in a matter of minutes or even seconds. So that's the biggest threat and problem with asymmetric. So let's look at some things that can go wrong with encryption, right? As I mentioned before, mistaking encoding for encryption. Hexadecimaling something, basic syncophoring it, that's not encryption, because it can easily be reversed back to plain text very easily. Also, the use of weak ciphers, ciphers that have known vulnerabilities. ROT 13 is basically what they call a Caesar cipher. So it's just a shifting of characters on the alphabet, easy to break. XORing is just, again, going through an algorithm that shifts it, and that is also easily reversed. Though it's used in many encryption algorithms, it's not the end result, and not ending there. And then you have broken ciphers like RC4 that have been known to have vulnerabilities, for decades. The other thing that I've ran into in my career is homebrew ciphers and proprietary ciphers. Though I have a math minor, I would not say I'm a cryptanalyst, and I would not write my own encryption algorithm. Though some developers choose to try to write their own homebrew or proprietary ciphers and algorithms, I would not recommend that. It takes years to come up with a good one, and as we just spoke about, many of them already have been broken, even though they've been around for decades. So this is an example that I actually ran into with this cookie username. So if you look at it, you can clearly see that something's off about it. It has J's, K's, 2's, and or some numbers, L's. It does not look computationally sound from a cryptography standpoint, but they've tried to encrypt it. And when you go through a test like this and you look at that, one of the things I like to run is this feature in Burp Suite, which is an intercepted proxy that we commonly use. And you can go through and analyze the entropy or soundness of the data. And you can see here that this shows 0 bits of entropy, which means it's not computational. It wouldn't be hard to reverse it and kind of like reverse engineer it and get it back to the data here. So yeah, I would definitely not recommend you try to write your own ciphers or proprietary or homebrew encryption algorithms. Use tried and true ones, as we'll talk about later in the talk. The other thing too that we run into is, especially when we're doing code reviews and the like, is the use of, so whenever you have a encryption algorithm, you need to start with seeding that algorithm. And usually this is with what they call initialization vectors and things like that. In the source of entropy and the source of that seeding of the algorithm is going to be dependent on the quality of the seed, right? And how strong that encryption is going to be. And with all these different languages that I've selected here, C, C++, there's a RAND, and then there's a SRAND. Random in Java versus secure random, and so on and so forth. And they just use stronger seeding for your encryption, which is going to make the cryptographic strength and the ability to break that encryption or reverse back to plain text harder. So insufficient seeding, such as using something very simple like a hard-coded value in your source code or just a timestamp. These are all obvious and easy ways to reverse if you're trying to break that encryption and again get back to plain text. Or using defective algorithms. Now, I don't think dual elliptical curve has been, I think it's pretty much been put out of commission, but it's just an example from way back, maybe a decade or more ago. But there was actually a controversy where the NIST, who controls the standards for these things, and obviously everyone knows the three-letter agency NSA, NSA coerced NIST into allowing this algorithm and kind of backdooring it so that they could intercept transmissions from our quote-unquote enemies, so they could leverage the vulnerability that they knew was there in this algorithm. So we talked about hashing before. One of the things that you definitely want to do with hashing, and we'll talk about this a little bit more, is what's called salting. So coming up with some random piece of information so that you can feed it into that hashing algorithm along with your plain text so that it's unique every time. So that if someone has the same password, if you use a different salt, then it's going to hash out differently. And this also helps defeat what I talked about, the rainbow tables. So if you have, computed, all common passwords or really everything in the library and the alphabet, into these rainbow tables, if it's salted, then that's not, your hash is not going to match. Also, you don't want to reuse that salt. So you want to have a different salt for everybody's password. Um, Also, you want to pick a random salt. You don't want to use something such as the username because that's really also obvious and not as secret if attackers trying to reverse that information. Um, and then concatenation, like as you're combining those, like the salt and the plain text before you hash it, you making mistakes there is another issue. Uh, Not all hashing algorithms are created equal, as I talked about before. Different encryption algorithms have been broken. MD5, as I mentioned, SHA-1 have what we call hash collision attacks. So the same two different pieces of information can be matched up with the same hash, therefore being able to bypass authentication or maybe some authorization, things like that. Um, Another issue is single round hashing. And what do I mean by that? So if you just run let's say you do salted, let's say you do, concatenate correctly, and then you pass that plain text in through the hashing algorithm just once, so single round, that's still not enough because computers, they've gotten fast, right? So they can break that even though they don't have a rainbow table for it. So what we try to do is make it hard on the attacker but easy on the user. And what I mean by that is, and we'll talk about this again more a little bit later, is doing multiple rounds of hashing, which makes it computationally expensive to brute force, but not computationally expensive for the computer to check it and log in. So convenience on the user, but difficult for the hacker or attacker. I don't like to use the word hacker. Hash length extension. I mentioned this before. So this is a way of taking the hash, extending it so that it looks like it's the same value that was hashed. MD5, SHA-1, as we mentioned, the usual suspects, these are vulnerable to that. And that's why these are deprecated hashing algorithms. Your SHA-224, SHA-384, SHA-512, these aren't vulnerable to that. So that allows like the plaintext and secret keys links to be known and makes it vulnerable. It also gives some insight to the attacker of the internal state of the algorithm at the time and can be computed. Additionally, and this is especially tricky with when you're using hashing to validate that what you're receiving is what was actually intended to be distributed. And so what happens is you can add additional data to the hash by extending that, and that's hash length extension. And as I mentioned, like this is mostly used for citing forged information. If you're trying to validate that what was hashed is the actual value, maybe prior to you performing some action such as authentication or authorization. And then, of course, talking about encryption, we have to talk about certificates. And we all know, like, SSL is dead, right? And a lot of TLS is dead, and a lot of hashing or encryption algorithms related to TLS have been deprecated. Um, but, we find other things other than just using, poor algorithms or, outdated um, protocols. Uh, not validating the expiration date, right? So a certificate has an expiration date when it's supposed to, be not accepted anymore. So not validating that. Um, Also, the common name. So there's a field called common name, as well as you can have other names in your certificate, but not validating that against, the to the authority that where you're trying to go is the actual server. Also, not validating the signing authority. So this is oftentimes what allows us to get a man-in-the-middle attack to work. Is intercepting, and they're not validating that signing authority. Um, and often during testing, we have to become that signing authority. Not warning users when you do, like, let's say you do these validation checks. Not warning the user that the certificate is invalid. Just going on about your business, whether it's self-signed certificate or if any of these issues above are there, and not warning the user. And then just plain coding mistakes. I find this all the time where, especially a developer might need to bypass, for testing, turn off checking, right? And then they forget to take that out of the code, right? And go back to actually checking. We find that a lot. And a lot of coding mistakes where they just don't get like the first bullet point right. They haven't checked it thoroughly or not using the right libraries and that sort of thing. Certificate pinning. So we see this a lot in, I've seen it a few times in when I do thick client assessments or like desktop application assessments, but we see this a lot with mobile application assessments. So just not having the certificate pinning there. And what certificate pinning is when the application launches, it has a certificate, right? Or usually an intermediate certificate or a hash of it. And then it checks that against where it's trying to communicate with. If these don't match, then, you know, no pass, no, fail, no, not going to work. It'll drop all the traffic and won't let you communicate with it. So oftentimes we have to either, bypass this or come up with another way to do our mobile testing. This is becoming more and more common, but there's still a lot of apps out there that we see that don't have certificate pinning. Google Chrome, for example, actually certificate pins a number of sites like Microsoft, of course, Google, and things like that already like built into it, so that it knows whether you're going to the right site or not, and will warn you or block you if it's not correct. Um, so as I mentioned with symmetric key, key management and key distribution is one of the biggest issues. So also one thing we see, especially with a lot of code reviews, we see that hard-coded keys are being stored with the in the code, or you have, like this has, some random text in front, but the rest of it is, pretty weak in my opinion. But storing that there allows an attacker, if source code is leaked or if they can, kind of brute force to figure out behind the scenes how it's working. We definitely don't recommend storing encryption keys in the code. And I talked about IV or initialization vectors when I talked about symmetric encryption. Reusing the same key in your application over and over, and a hard-coded IV. I'll talk about that a little bit more, what the IV is. allows for replay attacks, so an attacker can replay a transaction, and also leads to cryptographic oracles, which I'll dive into a little bit more here as well. Another one too, as I mentioned with encryption ciphers like AES, they have modes. So CBC, ECB, GCM. There's different modes for these on how they operate, and they have weaknesses. Some have weaknesses, right? So electronic code book, I haven't seen this in a bit, but this is definitely vulnerable to what's called block shuffling. And so let me explain the blocks, right? So a block cipher, as I mentioned before too, everything's broken down into little blocks and then padded, right? So ECB, each block is independently encrypted. So you get the encryption key, that block is encrypted, and you get ciphertext, and so on and so forth, as it shows in this diagram here. The way CBC mode works is, and this is why the initialization vector is critical. The key, so initialization vector and the key are fed into the algorithm, and that block is encrypted. Then the ciphertext that's spit out from there is used to encrypt the next block. And then that ciphertext is used to encrypt the next block, and so on and so forth. And so it's a lot more scrambled than ECB. And just to show you an example here, this is the plain text on the left. This is the image in the middle that's encrypted with ECB mode. And then on the right, this is one that's encrypted with CBC mode. You can see, after all, you can see the difference there. That the right one with CBC is a lot more scrambled up, and you can't tell what the original image is, whereas with ECB, you can still kind of get a gleaning on what the original content was. So I've seen this before too, no initialization vector. So that initialization vector is critical because that's what's going to feed in to allow that first block of text to be encrypted correctly, and so on and so forth. I've also seen the encryption key being used as the IV, as we talked about before, hard-coded IV, but also equally bad is using the encryption key as the IV because that's supposed to be like the seed, as I mentioned before. And that just, if you use the encryption key as the IV, it can lead to being able to discover the key, which renders all the encryption useless. So another issue is what we call with, especially with, if you don't have your IV correct, also with ECB, is what we call bit flipping. And that's where you take the piece of encrypted text and you just binary change the letters. So this image I have here, this is an example of that where you can see it progressively changes the characters in the value, and then I'm kind of looking for responses and seeing what I get back. And sometimes you'll get like a 200 versus like a 500 error code, and then you kind of have an indication that something's going awry. On this particular engagement that I ran a bit flipping because it was blind, I didn't really get any feedback. It was blind, but the next day, or even I think even the evening, I got this. So this was a storage site where they used to store data. And it was running on, I believe, Amazon AWS, and that's where they stored the data in S3 buckets. So as I was doing the bit flipping, that was the storage locations, right? And they kept a queue and a log, and that's how they knew how to move files from one place after they processed them, and so on and so forth. And as you can see, it says that the HIPAA servers went offline because the uploader was backed up because their queue had filled up and they couldn't identify what to move offsite. And here's an example of what they were getting. As you can see, so AWS is a Linux-based server system. And you can see that as I was doing the bit flipping, some letters got capitalized and some got, uncapped. And Linux, since Linux is a, case-sensitive operating system, it couldn't find the files anymore once they had, changed the bits on them. And so it couldn't remove the files, and the whole file system went offline on this storage server. So that's another vulnerability that you could have. I mentioned oracles before, so there are multiple different oracles. An oracle basically just means a way to glean information from the system that you probably shouldn't be able to get out of the system. And an encryption oracle is one of these mechanisms. So if you can feed it known plain text and you can get it to spit out the encrypted text, then you kind of control part of the equation because the plain text that you put into that value. And so that's the oracle, is that you're able to say, tell me how you encrypt this and what is the result if I give you this plain text. And it helps you glean that. And it can be even more devastating if you, here's an example. So I blanked this out to me. Keep the names of the guilty honest here. But you had the search keyword, and what would happen was that in the response from this, navigation text is an encrypted blob of text, and I would be able to glean some information out of the system by being able to control what that plain text was that was going to be encrypted and spit back out to me. As I said, it becomes even more devastating when you also have a decryption oracle. So we're going back to that example that I showed before with the username cookie. Again, you have some control over the information and you can glean more information about it. So you can get it to arbitrarily spit out decrypted text as well if you control that text. So here's an example of the response I would get. Currently logged in as blah, 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 a hexadecimal value. But I knew what I was feeding because I knew my username. And since it was encrypted, and I got to decrypt it, if I set an arbitrary username to whatever I want, I can get it to, decrypt that information, and that can be useful in further attacks. Another one, too, this is a fun one, called a padding oracle. As I mentioned before, there are different modes in Cipher, such as AES, one being CBC. One of the vulnerabilities with CBC is something called a padding oracle. And as I mentioned, CBC is broken down into blocks, and then whatever's left, they pad it to fit a certain size, right? So the padding oracle is a side channel attack, and it can allow you to completely decrypt and then re-encrypt information. Funny story, I had a client, a financial client many years ago that had cross-site scripting and SQL injection in their site. And I was asked to retest after they had done some remediation. Turns out what they did was they took the whole parameter string in the GET query and they encrypted it into one parameter How are they used? You guess it, AES, Cbc mode. And what I was able to do is use this attack, padding oracle, to decrypt, put my SQL injection payload back in, re-encrypt it, and send it off to the server. So congratulations, Mr. Client, you now have not just 2 vulnerabilities, but now you have 3. This was also notorious with like AES, or sorry, ASP.NET, Ruby on Rails, many other different systems. So just to explain this again, it's broken down into blocks, and you have to have a fixed size. If your size doesn't fit, then you add padding to make it to that size. If it needs 1 character to fit that size, you use a 1. If it needs 2, use 2 2s, 3 3s, or in this example, 4 4s. And that's how PKCS 7 padding works. So I'm gonna just let a video play here that will walk you through how the padding oracle works. So there's a tool called Padbuster, which is commonly used. You feed it in the URL with the parameters that you want. You give it the value that you want decrypted. You tell it the block size, whether it's encoded, whether it's plain text, hexadecimal, and sort of thing, and then parameters. So we'll let this play just here real quick. So what it does, how a padding oracle works is it's looking for errors and anomalies in the site. So when a padding is incorrect, does it give an error? Versus when the padding is correct, doesn't throw an error. So it's trying to do some analysis here of when it gets an incorrect error versus incorrect, correct error, or not correct error, but a correct response. And so as you see, there is one result of how they changed the padding just in a little way that yield them a 500 error response. And so from that, this tool is able to then go and manipulate the padding. And what they're going to do is start at the last block. Once they've gotten that figured out, then they're going to do the second to last block and go on from there, from there, from there. As you can see, as it's working, it's working on byte 8, then it'll work on byte 7, and it'll figure out when it's correct or incorrect padding, and from that, be able to manipulate the different pieces of the blocks, and eventually produce us the plain text result of what was encrypted. So I'll let this play here just for a second. And as it says up there, there's 9 blocks. It shouldn't take too much longer. But as I mentioned, one great thing about this tool is that it can not only be used to decrypt the data, but then you can use the same tool that once you have decrypted successfully, what it does is figures out the key from that kind of brute force method of the padding. And then you can use that then to re-encrypt the data. That's the attack I used on the financial firm, where I was able to reinitiate, because they didn't actually fix the SQL injection or the cross-site scripting. They just thought they had outsmarted me. So. Oh, okay. That looks like the video didn't finish. We'll move on though. I think I beat that. worse dad. So now we move to the end here. Like, what? Okay, so how do we fix this? If we're all failing at encryption, not all of us, but we see it failed a lot. How do we move past it? So, as I mentioned before, don't do proprietary or homebrew ciphers. Use proven, vetted algorithms, and keep up to date. Like I said, some have been broken, like RC4 and things like that. Like, move on to updated ciphers. Keep on top of that. Um, with hashing, use key stretching algorithms. So I hit on this a couple times. One is not using single round ciphers, computationally expensive cipher. You want to use computationally expensive. So PBK, DF2, bcrypt, scrypt. What they do basically is they'll run it through like 100 times, and you can feed in the amount, and so it makes it computationally expensive. You got to think if an attacker is brute forcing this, they got to run through the whole dictionary maybe or common passwords, and they've got to compute the hash and then feed it into this algorithm to check whether it's right. So you make it computationally expensive for the attacker, but very minimally, maybe half a second longer to log in, right? The salt, prepend a unique and random salt to the value before you go and do hashing. And this makes it even harder, especially if you're using the algorithms that I mentioned in the last bullet point for attacker, and also prevents them from being able to create as I mentioned, the rainbow tables, which is every value under that hashing algorithm. With symmetric encryption, as I mentioned, key management is the problem, right? So you got to practice proper key management. Keep track of your keys. We probably all share this, but we have the problem with our keys at our house. Our car keys. Where are the car keys? You keep track of the keys. Don't store them in the source code, hard coded, and that's the best way to approach that. And as I mentioned with the padding oracle, you use a better cipher mode. So the solution to that, and the reason why the padding oracle is successful, is because what we like to call, they're not using authenticated modes. I mentioned ECB, I mentioned CBC, but so yeah, you want to use CBC potentially definitely rather than EBC or ECB, but things GCM. What that is an authenticated mode, and what I mean by that is that it encrypts the data and then it generates a hash. So you can't do the bit flipping attack, because what it does is it checks the hash to make sure the original value matches that hash before it decrypts it, or that the encrypted string matches the hash before it decrypts it. So you can't have attacks like a padding oracle. Don't reuse encryption keys or initialization vectors, as I mentioned before. Sign encrypted text with an HMAC. So that was what I was talking about before with GCM. So you're authenticating the data prior to decrypting it. So if you want to use CBC, then you can. But you're going to have to do what GCM gives you for free. You're going to have to do an HMAC, which is basically doing the hashing, and then you're going to have to validate on your own. It's fine. You can do that. Do not directly display encrypted output, and this goes back to the decryption oracles. You can also randomize plain text prior to encrypting it. For asymmetric, again, you still have to exercise proper key management. And this is not obviously the public key is public, but this is more about the private key, because that's the one side you don't want the attacker to find. Going back to, again, the certificates, like the certificate name, the date, use valid certificates, strong key strengths. Make sure you're keeping on top of what protocols like TLS1, TLS 1.1, TLS 1.2, what's still recommended, what key strengths are recommended, like 2048. What algorithms? There's many different algorithms that have been deprecated. So what algorithms that you're using, and where you can, exercise the certificate pinning, either in your thick clients or your mobile applications, and use algorithms that support perfect forward secrecy. And what I mean by that is that if somebody does eventually capture the data that was encrypted, like over the wire or something like that, or stored somewhere, then if they can deduce the key, everything forward from that uses a different key. There are older algorithms that don't support perfect forward secrecy, and so once that key has been discovered, everything that's been captured can be decrypted. So here's just some different resources. A ex-coworker of mine, long time back, wrote a test bed called Magical Code and Checks Your Rainbow that helps you try your hands at different cryptographic attacks. There's a great OWASP guide available. This is a good white paper on padding oracles. There's a link here to Padbuster that I mentioned. And Bletchley is also the same ex-coworker that wrote the Magical Code and Injection Rainbow. He wrote a tool called Bletchley as well that helps you kind of navigate and exploit some cryptographic vulnerabilities. And so I encourage you all to check these out. With that said, I will be online here to take any questions, and welcome that, and thank you all for your time. Appreciate it.